Hi class, it's me, Mr. Morris, and we're going to continue in this Unit 1. This time we're talking about composition of mixtures. So we finished talking about composition of pure substances. Now we're talking about mixtures. Quick review. We want to look at each of these and decide if they are monatomic elements, diatomic elements, a compound, a mixture of elements, a mixture of compounds, or a mixture of one or more elements and or compounds. Okay, one or more element and compound. So the first thing that we see here is two different types of atoms, and they're all bonded together in the same ratio, so we know that that has to be a compound. So we put a C right here. Okay, the next thing that we see, we still have two different types of atoms, but since they're not touching, we're assuming they're not bonded together, so we would call this a mixture of elements. That's D. It's a sloppy D, but it's a D. Okay, the next one. I've got two types of elements that are touching each other, so those seem to be bonded together. And then I've got these two identical atoms that are touching each other. That is, so the white balls that are together are the that's a diatomic element. And then the other thing that you see in there, the other particle you see, is a molecule of a compound. So this is an element and a compound. We would put F. Number 3. So number 4, even though there's two atoms together, bonded together, it's just a diatomic element. So we're going to put B. Number 5. I've got two different types of elements floating around, and I also have one type of compound in there. So this is elements and compounds, a mixture of elements and compounds. And then over here, we've got a diatomic element and we got a monatomic element. So we have a mixture of elements, D. Hopefully that's a good review for you. This is something that we should definitely know. Okay, elemental analysis can also be used to determine the relative amount of atoms in substances to determine their purity. So we can analyze a mixture using elemental analysis. Let's look at some examples. The mass percent of iron in pure iron 2 oxide is 78%. Okay, so that's a fact we are giving you. 78% is pure iron oxide. Elemental analysis of an impure sample of iron 2 oxide, so this one is not pure iron 2 oxide, it's performed and calculated, and the calculated mass percent of iron is 73%. Okay, so we know it's not actually pure iron 2 oxide, and it's 73% iron. So what you always want to ask yourself is this percent higher or lower than expected? Well, this is a lower percent. It's a lower percent than what we expected. So then we have 3 different possible explanations that different chemists give on what this impurity might be. So chemist A says, I think it's because we have some unreacted iron in the sample. We need to decide if that's a possible proposal, and we also need to explain why. So let's think about it. If we have unreacted iron in the sample, would this percent be higher or lower? Would the percent of iron, would it be higher or lower than expected if we had unreacted pure iron in the sample? Well, that would lead to a higher percent. So having unreacted Fe in the sample, that means we've got more Fe than expected. That would lead to a higher percent yield. Percent of Fe. Percent mass of Fe. not lower. So this explanation is not possible. So this is not a possible explanation. Okay, it's not a good explanation for it. So let's look at the next one. Chemist B proposed that the impurity might be iron 3 oxide, which is Fe2O3. Is this proposal possible? Now this one's a little trickier because we have to actually look at the formulas. You see that FeO is a 1-to-1 ratio of iron and oxygen. Fe2O3 is a 2-to-3 ratio. Now if you're not real confident with your ratios, we need to get a common multiple. Actually, we want to do that anyway. So FeO, the ratio of Fe to O in FeO is 1-to-1, right? Or if we wanted to get a common multiple, we could say it's 2-to-2. If it's a 1-to-1 ratio, we could also say it's a 2-to-2 ratio. In Fe2O3, it's 2-to-3, which means a 2-to-3 ratio in Fe2O3, that is a lower ratio of iron. It's a lower percent of iron. So what we can conclude is that Fe2O3 has a lower percent Fe. It's a lower percent Fe. Now, is it possible that having excess Fe2O3, having Fe2O3 present in the sample, could lead to a lower percent of iron in the sample? Absolutely. So this is a possible explanation. All right, chemist C proposes the impurity might be nickel 2 oxide, NiO. Now, is there any iron in that at all? There's not, okay? There's no Fe in NiO. But NiO would increase the amount of oxygen. It would increase the amount of the sample. So if I had some extra NiO, then the molar mass, or the mass of our sample that goes on the bottom in the denominator of our fraction would be greater, which would make our percent go down. Okay, so we didn't add any more Fe, but we did add something else. So this is a possible explanation. Because it would decrease the percent of Fe. All right, kind of a tricky concept. Make sure that you understand that. If you don't, work through a few example problems and then and let me know how I can help you if you have any questions. We're going to go down into a slightly different type of problem. This is a little tricky, so bear with me. We have a 5-gram sample containing glucose. It's important to recognize it's a 5-gram sample containing glucose. It is not pure. That's the amount of the sample. It was reported to be 25.0% oxygen. Now, if we're assuming that there's no oxygen present in any of the other impurities, we want to calculate the percent of glucose in the sample. Now, if we want to know the percent glucose, then what we need to know is the mass of glucose over the mass of the sample, and then we need to multiply by 100. We need to know this before we even get started. What are we looking for? Mass of the sample, I already have, it's 5 grams. Remember, it's not glucose, that's the mass of the sample. So what I need to know is the mass of glucose. How in the world am I going to find the mass of glucose? Well, all I know is the percent of oxygen. So what I'm going to do is find out how many grams of oxygen that is. Well, they gave us the mass of the sample, so let's get started by doing this. I've got 0.25, that's 25%, is 0.25 multiplied by 5.00 equals, and that's going to tell us the mass of oxygen. So 0.25 times 5.00 gives you 1.25 grams of oxygen. Okay, I'm going to start with that. 1.25 grams of oxygen. I want to know how many moles that is. So I know 16.00 grams of oxygen is equal to 1 mole of oxygen. But what I'm really trying to find is the mass of glucose. So I don't just need oxygen. I want to know how many moles of glucose I have. We've got the formula for glucose up here. So we're going to go how many moles of oxygen there are in a mole of glucose, C6H12O6. Well, I hope you can see that we've got a subscript of 6 on the oxygen, so there are 6 moles of oxygen in 1 mole of glucose. Okay, that gets us that far. We want to continue on by converting from moles to grams. I need mass of glucose, so I have 1 mole of glucose, C6H12O6, is how many grams of C6H12O6. So to figure that out, we need to multiply the mass of carbon, 12.01, times 6 plus 12 times the mass of hydrogen, which is 1.008, plus the mass of oxygen, which is 6 times 16.00. I end up with 180.096 grams of glucose in 1 mole. So then we just plug this all into the calculator. 1.25 times 1 over 16 times 1 over 6 times 180.096 over 1, and I end up with 2.35 grams of glucose, C6H12O6. So my percent of glucose is the amount of glucose, 2.35 grams, over the amount of the sample, which is 5.00 grams, times 100, 2.35 over 5 0.00 times 100, and I get 47%, 47.0%. Okay, a couple things just as we go back over it. So what we need to know is we can only do this if no oxygen was present in any impurities. In other words, all of the oxygen in our sample definitely came from glucose. There's no other impurity that could come from. So I can rightly assume if I know the percent of oxygen, I could find out how much oxygen there is by multiplying by the sample. I could take that and convert to moles of oxygen. If I know the moles of oxygen, then I know how many moles of C6H12O6 there were, because we know that all of the oxygen came from this. And there are 6 moles of oxygen for every 1 mole of C6H12O6. And then we could use the molar mass to find the number of grams of C6H12O6. It's a question that you definitely need to know how to answer. So we'll have some similar questions in the practice. Make sure that you follow up with that and ask questions if I can help you understand it better. All right, then we have a mixture. Number 3, a mixture contains only NaCl and Al2SO4 A 1.450 gram sample of the mixture is dissolved in water, and an excess of NaOH is added, producing a precipitate of AlOH3. An excess of NaOH. Now, when that happened, if we have an excess of NaOH, that means all of the other thing, whatever the reaction is that's happening, the other reactant is consumed. Well, if I have AlOH3 that is produced, so it produced a precipitate of AlOH3, well, that tells me that aluminum is the thing that reacted with the hydroxide, not sodium, not chlorine. Aluminum is the one that reacted with this. So I don't really care too much about sodium chloride right now. I only care about the aluminum sulfate because it is going to be completely consumed to make aluminum hydroxide. Okay, then the precipitate is filtered, dried, and weighed, and the mass is 0.107 grams. That's the mass of aluminum hydroxide. Now we want to determine the moles of Al3+ in the precipitate. Well, if I want to find the moles of Al3+, first I need to find the moles of AlOH3. Well, we've got our mass of AlOH3 as 0.107 grams of aluminum hydroxide. We need to go ahead and put our molar mass down. So aluminum has a mass of 26.98. And then we have 3 times the mass of oxygen, which is 16.00. And 3 times the mass of hydrogen, which is 1.008. That adds up to be 78.004 grams of aluminum hydroxide. In every 1 mole of AlOH3. Technically, it didn't ask me for the number of moles of AlOH3, though. I want to know the moles of Al3+. Okay, so for part A, which is what I'm answering here, I need to find out how many moles of aluminum ions there are in 1 mole of AlOH3. Well, I only have 1. And you might say, well, I don't really need to do that, do I? Well, in a calculator you don't, but you do have to show it on paper in order to justify this. So really, 0.107 divided by 78.004 is essentially what we were doing. You could do that times 1 over 78.004 times 1 over 1 if you wanted to. Either way, you're going to get 0.00137 moles of Al3+. That's part A. Part B, determine the moles of Al3+ in the mixture sample. Well, since NaOH was in excess, and AlOH3 was the product, then all of the Al3+ ions were consumed. In the reaction. Since we can assume that all of the ions were consumed in the reaction, we can say, therefore, the moles Al3+ in the reaction mixture must equal Al3+ in the product. So what we're saying is Al3+, the moles, or the N of Al3+ equals the same number, 0.00137 moles. So that's the answer to part B. We've already got that. So if we know that, could we find the mass of Al2SO43 in the sample? Well, sure we could. We got 0.00137 moles of Al3+. So I need moles of Al3+ on the bottom. All right, and we want to relate it to Al2SO43. So moles Al2SO43. We need to know the relationship between these. Well, I have 2 moles of aluminum ions for every 1 mole of Al2SO43, but I want to know the mass of it. So we are going to multiply by the molar mass over 1 mole of Al2SO3. Al2SO43. All right, and aluminum again is 26.98 times 2 plus S times 3. So we're going to do 3 times the mass of sulfur, which is 32.06, plus 12 times the mass of oxygen, which is 16.00. We end up with 342.14. grams of Al2 SO4 3, and then we would be able to find our answer, 0.00137 times 1 over 2 times 342.14 over 1, and you end up with 0.234. grams of Al2 SO4 3. All right, we got one more part to this question. Calculate the mass percent of Al2 SO4 3 in the mixture sample. So now we have the mass of Al2 SO4 3. We have the mass of the sample. So then we just need to divide and multiply by 100. So part D, and I should label this right here as part C, sorry. It's part C. Now part D, we are going to take the amount of aluminum sulfate divided by the amount of the sample, 1.450, times 100, and you end up with 16.8%. Okay, we're combining a couple topics here. We combined elemental analysis with our knowledge of mixtures and did a few examples of AP level problems. Make sure that you go through these notes, work back over them. If you had something you're confused about, feel free to ask questions about it in class. And of course, try your hand at a few of the practice problems.